All right. So this is called an attempt to formalize counterpossible reasoning in deterministic settings. The paper actually has 2 attempts. I'm only going to talk about one. The idea here is if we want to make an agent that makes good decisions, we not only need to give it a good model of what actually happens in the world, but a good model of what would have happened if it had done something else. And if we imagine this situation as having a deterministic program running on a deterministic computer in a possibly deterministic physical world, we sort of need to answer the question, what would have happened if this deterministic algorithm had actually done something different? And that's what I want to talk about in this talk. So there are going to be two parts. The first part is going to be what's the problem? Why isn't this problem trivial? And the second part is going to be an attempt at going in the direction that we think is promising. So in order to make decisions, you not only need to know what is going to happen, but what would have happened if you had done something else. And so we can see this step when, in the step from Solomonoff induction to Markus Hütter's AGI. Solomonoff induction uses the simplest explanation of what actually happened in the past to predict what will actually happen in the future. And this is guaranteed to converge to the true environment if this true environment is computable. Guaranteed to converge to making correct predictions. AGI uses the simplest explanation of what actually happened in the past to predict what would have happened by saying, let's make a model of the environment, something that takes as input what you do, and we can only input what you actually did in the past, and then the thing that best predicts that, if you put in something else, says what will you do in the future. This is not guaranteed to converge by the same strong convergence results because you only see what you actually did, and it could be that the model that you're converging to always agrees with what you actually do, but doesn't agree on things that you don't do. Given this, and given some things that I'm going to talk about in the next 2 slides, we have to ask, is this thing that AGI learns the right definition of what if? Our motivation here is not necessarily to say it's the wrong definition. Our motivation is to say, if it is the right definition, we want to know why, and we want to really understand what is it going to do, what sorts of things it's going to do, and why can we expect it to be correct. So there are 2 reasons why we think this deserves a closer look, whether this is correct. And the first one is that AGI sort of if you look at it naively, that's not the only way to look at it, but if you sort of look at it naively, it sees the agent here, the environment here, and a discrete input-output channel from here to there. And that's not what happens in the real world. In the real world, you have a computer that's just in the environment. And so the question is, does this give rise to the right things? So things that can happen in the real world is that an agent's actions, if the agent drops an anvil on its CPU, then bad things happen. And again, AGI might do the right thing in this situation, but it's not obvious from the model where you define what happens by this discrete input-output things. And the other way around, if the agent heats up while it's making a decision, that might affect how the environment interacts with it. And there's also the question of how do you actually define the counterfactual world where AGI outputs something else, or whatever we actually use outputs something else. Which transistors in the CPU do we change in order to make it so that this thing outputs something else? How do we actually construct the world where we now have a computer that has outputted something else? And I think that it's important to keep in mind here that if we want to construct a super intelligent agent, a smarter than human agent, we have a different situation than we have when we have the kind of simple inference algorithms that we generally use today, because a smarter than human agent might be just as able as we are to figure out that it is made out of transistors. and we want to understand like how is the definition of what if going to interact with that knowledge. And so like it seems to us that like the question that we would like to ask is what would happen if a deterministic subprocess in a deterministic physics returned a different value than what it actually returns. And given like what we think is the right thing, right way of answering that question, we can then ask, is like the thing that AGI actually learns the definition that we want? So here's a more specific reason to like think that this issue might be a problem. So you, like probably most of you, all of you maybe know the prisoner's dilemma. One way of thinking about it is two agents can each choose to pay $1, and which we call cooperate, and if they pay $1, then the other agent gets $2, and that's all there is to it. And here we're going to consider a version of the prisoner's dilemma where we have two artificial agents, two computer programs, who happen to exactly know each other's source code and know that they happen to make decisions in the exact symmetric way from each other. So whatever we like say is the correct definition of what would happen, both of these agents use that and try to maximize the amount of dollars that they get. And so if we look at these agents, and if they are intelligent agents and look at each other's source code, they can see that each is going to cooperate if and only if the other one does. Now, classical game theory does in fact say there's common knowledge of rationality, which means that both agents do in fact know that the other one makes decisions in the exact same way. But classical game theorists conclude, well, if my opponent cooperates, it's better for me to defect, and then I get $2 instead of $1. If my opponent defects, it's also better for me to defect. I get $0 instead of paying $1. So it's better to defect. But like intuitively, if we know that my opponent is going to do exactly the same thing as I am going to do, then I should reason that if I'm going to cooperate, so does my opponent. And we at least find that line of reasoning pretty compelling. And if you take the naive model of AGI as like this thing that interacts with the world, but we now imagine that there are two AGIs, and we say, well, like I changed the world by changing what I output without changing what my opponent outputs, then the result would be that they defect. Again, like this is not necessarily what AGI actually learns, because AGI doesn't, can't in fact learn that there's another AGI in the world because it only entertains computable hypotheses and it's not computable. So in fact, it's very likely that, I think it can be shown that what it does learn is to cooperate just because it sees a world out there where it thinks, well, I'm seeing whenever I cooperate, like I get $1, and whenever I defect, I get nothing, and that's the whole world. But what's troubling about this is that even if this gives the right result, it seems to give the right result for the wrong reason. Because the agent does not actually understand how the world works in this case. It simplifies the world to something that says, well, I don't have an idea that there's another agent there, I just see that if I cooperate, I get $1. And then if that's like the answer, we have to ask, like with an actual super intelligent agent that we implement, if the agent is actually able to figure these sorts of things out. And if the situation is more complicated than this simple thought experiment, does it do the right thing? And we want to understand, like, what is the right thing? And how can we formalize it? How can we make sure that an agent does that thing? So here's our attempt to, like, formalizing what's right, which doesn't quite work, but we think goes in an interesting direction. It may lead to something good. So again, like if we think of the problem as deterministic subprocess, and we ask the question, what if that returned a different value than what it actually returns? So my intuitive argument used abstract reasoning. I didn't say, like, I didn't compute out what does my opponent do. I said, like, by looking at me, by looking at my opponent, I can see that whatever I return, my opponent also returns. So it's sort of like when you write a sorting function, you don't like check whether the sorting function is correct by like mentally plugging in every possible list and checking that it gives the right result. You have some abstract reason to think, aha, this is the right thing. And I think it's like very likely that realistic general intelligent agents will use this sort of abstract reasoning in all sorts of situations, like when they need to like figure out how to build artifacts or how to write computer programs and so on. And so now, some of you who like have seen some of our papers, like something that a lot of people like ask me is like, why do we use a lot of formal logic? And so I want to argue that like in fact formal logic is a good way of approaching this problem as I've set it up, because like I think that what intuitively you want to do in a situation like this prisoner's dilemma situation is to use abstract reasoning. And I think that the best mathematical model that we have today in order to try to start analyzing what does abstract reasoning mean, the best mathematical model of that is like formal logic. So even if I don't think that an artificial agent is going to use formal logic for most of the situations that it faces, I think this is like a good way to try to like start today to ask the question of like, how should it reason abstractly? And so here's something. UDT stands for updateless decision theory, which was suggested by Wei Dai, which is the idea of like ask the question of what would happen if my deterministic program returned a different output based on some notion of like what would happen if the laws of logic were different or something, which Wei didn't formalize more. And this version is like a version based on formal proofs proposed by Vladimir Slepnev. I sort of glossed over the word counterpossibles in the title of the talk is the philosophical word for what if not just the facts about physics were different, but the laws of logic were different. So here's how this algorithm works. I have like the example of the prisoner's dilemma. I have two agents, A0, A1, which are deterministic programs, which have utility functions U0 and U1, which are also like deterministic programs without arguments that are written by quining the source code of A1 refers to both the source code of A1 and of U1. Clean second recursion theorem is the formal way of showing that this is sort of like okay and can be done. So U1 just implements, like if I cooperate, then I pay $1. If my opponent cooperates, I get $2. And my actual utility is like the amount of money I get minus the cost. And here's how the agent works. The agent like loops, goes through all the possible outcomes from best to worst. So $2, $1, $0, lose $1. For each outcome, it looks at each possible action, cooperate and defect, and it checks whether piano arithmetic proves that if this agent takes this action, so for example cooperates, then it gets this outcome, for example gets $1. And the first time it succeeds in finding a proof like this, it returns that action. And so, for example, in our example, like we can prove that if we cooperate, our opponent also cooperates, so we get $1. If we defect, our opponent also defects, and we get $0. And if these are the only things that we can prove, then we are going to cooperate, because that's the first thing we find. In order to literally implement this, you would need a halting oracle. You can do without a halting oracle, you can do approximations, and you can also do like something with modal logic that allows you to figure out what the thing with a halting oracle would do by a computable algorithm, but I don't have time to go into that. So what's worrying about this is that we are finding these implications which are under false premises. So, for example, if it were the case that the first agent defects, then it would be true that if it cooperated, it would get utility -1. Because, like, if you have a false assumption, then every conclusion follows from it. So it seems to be consistent that actually, like, we can the agent defects, which we think is wrong. And still and the reason it defects is because it thinks it would get a penalty if it cooperated. And actually it turns out that this can't be the case. And the reason is, like, suppose that this were provable, we can also prove that we get $1 if we cooperate. We can prove both of these things if we can prove the other thing, that we get a penalty. Then we can prove that we don't cooperate, but then we can also prove that if we cooperated, we would get $3. And then in the loop, like the first thing that we check is if we cooperate, do we get $3? And if so, then we cooperate. So under this assumption, the loop would terminate right there, the agent would cooperate, and then that would be a contradiction to our assumption that we can prove that it doesn't cooperate. So that was a bit fast because I'm out of time, but like this implication is not provable. And in fact, in this case, only the implications that we want are provable. A way to think about this is that piano arithmetic has multiple models, which are sort of possible worlds which satisfy the laws of piano arithmetic. One of these is the actual true world, and the other ones we can see as like impossible possible worlds that sort of like are alternative worlds. They may not be a great notion of impossible worlds, but they are a version of impossible worlds where in fact there are such worlds where the agent defects and there are worlds where the agent cooperates. And this means that you don't get these sorts of vacuous conclusions. There's an example which I don't have time to go through in detail, but just to say that this is not perfect. There is like something weird where the agent can choose to take either a $5 bill or a $10 bill, but if it takes the $10 bill and piano arithmetic happens to be inconsistent, then its money gets taken away. It gets a fine of $10. So in this case, it actually turns out that this algorithm that I showed chooses to take the $5 bill, because even though in the real world, in the actual world, piano arithmetic is consistent, it turns out that you can prove with some work that in all the impossible possible worlds, according to my definition, where the agent takes the $10 bill, in all of those worlds, piano arithmetic is inconsistent, even though it isn't in real life. And so you get some weird situation where, like, if you take the $10 in those impossible possible worlds, you would get nothing. So in short, like, this is an attempt to, like, clearly I haven't shown you like a satisfactory account for what does it mean to like do counterpossible reasoning, what would have happened if the algorithm returned something else. But like this is sort of interesting enough that we think it's like worth thinking about. So we think that this is like there is no guarantee that there is a correct solution, that there's a better solution. Well, there's a better solution because there's something that we would do if we had more time to think about it that wouldn't be this crazy. But there may not be like a solution that satisfies all the desiderata that we might write down. What we want is sort of to figure out the best thing there is, and we think that this is like a useful step towards figuring that out. Thank you very much.